Good afternoon, everyone. Welcome to this session around AI in veterinary. We'll be getting started in just a few moments. We'll just let people join from their various meetings and so on. So please do make yourself comfortable, get a cup of tea, and we'll be getting started in a couple of minutes. Hi, and to those that have just joined, welcome to this webinar session around AI in veterinary. We'll be getting started in a couple of moments, so just bear with us while we allow people to join from their various meetings or lunches that they might have had, and we'll be getting started in a second. Hello to those that have just joined. For those that have been here since the beginning, they'll be sick of me saying this, but we'll be getting started in just a moment. We'll just let people join from different meetings, so please just get yourself a drink and we'll be getting started in a moment. Okay, brilliant. I think it's been a few minutes now, and I'm sure there'll be people joining as we go through the session. But good afternoon, everyone, and welcome to this session around AI in veterinary. We're all really delighted to have you here for this session. Just before we get started, we are recording this session to use, so please let us know if that will be a problem in any way. As you'll see that you are muted and camera off because it is a webinar, but there is the Q&A function, so please ask questions throughout the session and we'll have some time at the end to ask Davide all your burning questions around AI in veterinary. So without further ado, I'll introduce myself. Hi everyone, I'm Sarah Aitchison, the VHive Incubator Manager, running this session today in collaboration with Leica. So in terms of what the VHive Incubator is, we're a strategic alliance between the University of Surrey, based in Guildford, about 40 minutes southwest of London, and Zoetis, the world's largest animal health pharmaceutical. We're the UK's first incubator for companion health and livestock health, supporting early stage companies to be able to get to the market more quickly with the best product possible. We support companies around the globe, of which Leica is one of those great companies, providing bespoke mentorship, workshop, and kind of networking support, all based around the animal health ecosystem. So here's a few of the areas on the screen around how we support the companies. But if you're interested in learning more, I will be sending an email follow-up later, where you'll be free to get in touch with myself to learn more about the programme. So without further ado, I'm now going to pass over to Davide Tricarico, who is the CTO at Leica, who's going to be running this session today around using AI in veterinary, a deeper dive of what AI is and how it's used, as well as an exciting overview of how Leica are using AI in the veterinary sector. So without further ado, I will pass over to him.
Hello everyone, thank you Sarah. Thank you for so many people. It was not expected. So thank you everybody. So let me start sharing the screen because I prepared some slides. So okay, perfect. Oh, I'm also recording the presentation, so you will have multiple recording of this presentation. So let's start from who I am, okay? Because Sarah was so kind to introduce herself, so I would like to do myself the same. So I'm Davide. I work as CTO in AITEM, so I'm leading the development team. I hold PhD modeling and data science, and I am a computer engineer. You can contact me whenever you want to this email, okay? And I have some experience in the field, especially in the software engineering, okay? Let's see what we are going to see today, okay? Maybe it's more interesting than myself. So we will start a bit of introduction. Okay, we will see how the AI evolved during the years. We will try to set up some ground knowledge about the different kind of sets that we have in this field. We will look under the hood to see how the machine learns and how they works. And especially, we are going to see what is into the so known LLMs. And in the end, I will show you a practical application that is Laika, so the tool that we developed for the veterinary AI. Little disclaimer, okay? So especially for the ones that maybe are very prepared, I'm trying to stay shallow, okay, on the concept, even if they are a lot. I will do a lot of oversimplification, but I open to answer the question that you will have. Maybe not in the time we have, but you have my email, you will have my email, and so you can also ask me or contact me on LinkedIn. Okay, so keep this in mind. So let's start. Okay, so and what better than starting from the definition, also some of the definition of artificial intelligence. And you can see that we can try to make everything starting from Alan Turing, well known, especially in the UK, the genius that also helped to solve the World War II. And also I took the definition from Wikipedia. Okay, so something from the very beginning and also something from the nowadays. And you will see that in the end, some particular aspect emerge because we always talk intelligence, but we always talk about science and engineering, okay, and machines. So those are the ingredients. We will come back to this introduction, to this definition later, but it's just this for an introduction. And okay, you will see many memes in my presentation. In this case, it was just a joke about the fact that sometimes from the outside seems like magic, but it's not because it's really science and engineering. So have solid background in what is happening. So let's see a bit how evolved. We said that everything starts from let me say the 50, okay, the year 50s, with what is called a symbolic era. Okay, so when we talk about symbolic, we mean that the AI application were really written not just to learn from the data, but was really hard-coded by experts of the matters that set up rules and say, okay, if this, then this, if this other, then this other, and it's really the beginning, okay? So there are several applications. Most usually are referred as expert system because they are based on experience. Then in the 70s and the 80s, with the advance in the technology, in statistics, and all the machinery, or the mathematical machinery that is behind, and also with more powerful computing machines, it started what is called the data-driven approach. So instead of determining arbitrary rules for taking decision and making the task, the application starts to have data to learn from. Okay, so they exploit some patterns, some correlation between the data to do the task that they have to do. And this is the burn of the machine learning. Okay, what is called actually machine learning. Then everything seems like was a boom. Everyone was super happy about what is happening, lot of expectation. But then there was a period of time that was almost 20 years that was called the AI winter. Okay, so it was a moment where the extremely high expectation driven by the preliminary good result that was in the data-driven era had not matched the real result that the system obtained. Also because the expectation, you see here, I put, Terminator machine, because the expectation was also driven a lot by science fiction, by all the romance, all the literature that was about, okay, we are going to have AI doom, or we're going to have super intelligent systems that are going to coordinate everything. But this was not true, okay? Especially because at the time there was still missing some bricks that are the nowadays foundation of the AI boom that we see. That will arrive in the 2000, okay, especially in 2010, around these days, where really we have the data, because you remember that in the last years of the 90s and the beginning of the 2000s, we had the .com. Okay, that was at the end is famous because it was, I mean, failure, a financial crisis because of the .com. But apart from the financial aspect, it was an entire movement that driven many applications from physical to computer. Okay, and so this makes that many data, much of data that was in the 80s and the 90s was on the paper, okay, was moved to computers. Okay, so this transition is really important because we have said before that these AI machines are actually machines, are computers, so they cannot read paper. Okay, they read bits and bytes. So having data in bits and bytes is one of the enablers for doing that. But the other enabler was the advancement in the hardware. Okay, because, and here you see the image of NVIDIA, actually, because it's one of the cornerstone of this story. The rise of the GPU and the hardware capable of doing so many calculations moved everything to a scale that was impossible before. So basically, the expectation that they were in the 80s that was not possible to achieve in the 80s with the technology and the data available, suddenly became possible in the beginning of 2000. Okay, and then, I mean, we are more near to the nowadays. We moved to okay, in the 2000s started deep learning, so these big models that learn from many data on big hardware, muscular machines, and etc. We move to nowadays where we have the so-called generative AI, where well, the paradigm is a bit of change. We will see later in the when I will put some ground foundation on the terminology, where we move from having machine doing specific tasks to having machine actually creating data. Okay, so creating content that was a task that was not really in the hands of the machine so far. Okay. And okay, the reference here is the well-known ChatGPT application. It was one of the first. Okay, that was one of the first known to the general audience. Okay. Spoiler, of course. I mean, I oversimplified the progression of the history of the AI, of course, as a line. Okay, but I think that it's more like something that that is the tube map, because you have different branches that actually intersecate each other, one cross-pollinated the others, and they evolve, okay, together. Okay, good. Again, the definition that we have seen at the beginning, but now I would like to go a bit more into the definition, okay? So the definition is a point of start, of course. You see that here I highlighted the fact that one of the key foundation of all the AI movements is the science and engineering, and the fact that they are computational systems. No, they cannot be mechanical systems, they are not hydraulical systems, they are not biological systems, but they are engineering and computational systems. Okay, and you see, I mean, the three foundational in the mathematical part, in the statistics a lot. Okay, and the computer science. Okay, we always talk about these three domains in the end of the AI. The other aspect that I want to highlight in the definition is that every time we say, okay, we have artificial intelligence, intelligent machine, intelligence, we have to, okay, put a frame on what we are defining as intelligence, because there are books and books in philosophy, okay, or what is the intelligence, how it's defined, how we can measure it, and etc. But there is not a common, okay, a common ground in this. There is not a general acknowledgement, okay, an agreement among the world about what is intelligence. So the smart thing in the definition is that when we talk about artificial intelligence, we always talk about in comparison with human one. So when we talk about an artificial intelligence system, we are talking about a system that can do something that the human can do, okay? We are not talking about artificial intelligence in case of a crane, okay? Or another machine like a car, okay? A car, from the perspective of moving through the road, is not an artificial intelligence system, okay? Because moving on wheels is something that humans doesn't do. Okay, the human cannot do it, so it's not an intelligent task from the human perspective. When instead, if you look at the car in the autonomous driving, it is an artificial intelligence system from that point of view, because it's doing something that human do. So it's taking decision on the road based on the perception of the space around. Okay, and from that point of view, is an artificial intelligence system. From the point of view of just moving the people in the world, is not, because it's a tool. Okay, it's not intelligent from this point of view. So with this in mind, let's try to clarify a bit, because a lot of times you can hear artificial intelligence, and you heard about machine learning, you heard about deep learning, you heard about generative AI, natural language processing, and many others, and it's not always clear what is what. Okay, so I'm trying here in these slides to help you to give the tools to understand what is what. Okay, so everything here, the superset of everything, is of course the artificial intelligence tools, okay, and methods and algorithms. And in this set, you have everything. Okay, so the whole machine learning, deep learning, and generative AI is all in the artificial intelligence set. But there is a difference between what is into the machine learning and what is outside from the machine learning. Machine learning is the first set in this picture. So I anticipated it a bit before. So outside from the machine learning, we have all that artificial intelligence method, because they are still mimic and trying to replicate and perform actions that are from human. Okay, because you can have in artificial intelligence system able to diagnose disease with an algorithm. Okay, and diagnose disease is something that human do, and so an algorithm that do that is somehow an artificial artificial intelligence application. But what is outside from the machine learning are those methods that are based on expertise. So if you want to design a diagnostic algorithm, then you go to an expert, maybe in, I don't know, the disease that you are trying to make the algorithms about, and you ask, okay, what are the rules? Okay, what are the inputs? How can I do that? And you just write down the algorithm to make it. Okay, but it's an explicit algorithm. Okay, and is fixed and is based on the expertise of the person that is doing that. On the other side, inside the machine learning, okay, you have what is called the data-driven approach. Okay, while instead of giving you the data, the rules to the system, you are throwing basically to this method a lot of data. Okay, and in those data, maybe there are all the data that correlate some particular aspects with the disease. And so the system is able to find the magic formula that links these evidences to the disease without anyone saying to the system how, but just say, okay, those are the data, those are the expected output, try and find a way. Okay, so this is really the difference between what is inside machine learning and what is outside. In the machine learning, of course, it comes a lot the patterns recognition, okay, because is everything about patterns in the data, and the statistics, of course, because they are always relying on statistics. Here's an example. So when we talk about arbitrary rules, we talk about an algorithm. So here you see decision tree that has been defined by a human, by an expert human. You will see everything here is reasonable. So you see, is the palpable pulse, yes, no, and then depending on the answer that you have about that question, you arrive to a decision. On the other side, you can do the same. So you can do a decision tree, but completely based on the data. Here you see this is a decision tree that is classifying the flowers, okay, some flowers among 3 classes. And you see that the rules that are here are much less human than the one that you see here, okay? And this is true because the model found that based on the data that you provided, it found that there is an optimal switch between the different conditions, okay? Those are two different algorithms. Okay, I'm not going into the details now, but this is basically the decision tree. This is another approach that is called support vector machine, that instead they divide the space of the input between the different classes, recognizing some mathematical properties of the data. Okay. In the field of the machine learning, I decided to put one slide about the neural networks, okay, because they are really popular, they are really powerful. They are not always the perfect decision for a problem, because sometimes a simple algorithm is enough, but they are really the foundation of the entire bloom of AI that we see now. Neural networks comes into the machine learning, okay, in the machine learning family of methods. They are inspired by our brain, okay? Here the inspiration is about having a network of nodes that communicate each other and influence each other. The system is meant to, you see here, okay, the very basic, so the single, let me say, node that is called the neuron, okay, this is not really a neuron, but it's a node in the network, is doing a very simple operation, because it's just summing up the inputs weighted by some numbers. They are summing up, and there is a function that is squeezing the value between 0 and 1. That's all, okay? The entire intelligence of the system is in deciding correctly these weights of each of the node of the networks. Okay, everything done. Okay, so by putting together thousands of these nodes, or millions or billions of these nodes, it comes out the artificial intelligence that you use every day. Okay, so everything is based on this. It is very good in high-dimensional data, because the bigger the network, the more they can get strange patterns in the data. Of course, the more it grows the network, the more it grows the numbers of parameters to be learned. And so you need more data. Okay, you cannot train a very big model with few examples. And basically, it is very powerful. Okay. And is that the basic of the deep learning? And now we see, okay, so we talk about deep learning, but what is the difference between deep learning and the machine learning? Okay. If you remember, before we move from artificial intelligence to machine learning, by not having anymore a human defining the rules, okay, and having the system defining the rules based on the data. There is still one point that is up to the human in the machine learning. That is, okay, but what are the inputs of the model? This is again solved. Okay, there is no more need of human in the deep learning. So in the machine learning, you have to still saying, okay, I'm not going to tell you how, but know that based on these inputs, you have to understand what's the output. Okay, and there is an entire set of models and algorithms to understand what are the important inputs, okay, in a problem. For example, imagine that you have to build a system that predicted the cost of an house, okay? So you can reasonably think that the dimension of the house is one important input, that the year of building is another one, that the zone of the city is another important one, and you can also reasonably think that maybe the color of the house is not that important, okay, to understand what's the cost of the house, the estimated cost of the house. So you can decide to build a system that is just using the one that you think they are important, okay? And this is basically say the basic of machine learning. So you do system in this way. The operation that I told you to understand what is important or not is what I was saying, the feature engineering, so that is a complete task. But imagine instead that you don't have that simple data, okay? So you don't have a problem in which is clear what is important and what is not, or at least with a bit of expertise, you can understand what is wrong and what is not. But you have a problem like a picture. You have an input like a picture. Okay, so a matrix of pixels or a volume. Okay, a CT scan. Imagine a CT scan for the one that knows it's a volume. Okay, so it's a lot of information. It's hard and is also not really working to arbitrarily define what are the pixels to see in the picture. Okay, because the picture can change, they can move, can be completely different, and it's also really impossible to say what is that. So here it comes to deep learning. Okay, deep learning is one step more in the independence from human intervention, because it's a set of tools that you just throw the data to it, okay, and they will find a way. Okay, they will decide what is important and what is not. They will define what is to be considered and how to solve the problem that they have to solve. Okay, so it's like, okay, I'm going to have a big mass of picture and I will throw to this method and they will find a way. Okay, they will find what to look in the picture. Okay, you see here, okay, in this picture a description of what I was saying before. So you see that in the machine learning you have this feature extraction step in which you define what are the meaningful inputs to build that is a classifier between car and not a car. So you're manually defining the features, so the inputs of your network. While instead in deep learning you get rid of this human intervention, you make a model that is bigger, and you will ask that model to do the job of the person, okay, of the expert. That is going to do exactly the same, okay? That is going to do the same without having the human intervention in it. One, as you have seen maybe from the previous slide, you have an extension. The model is bigger in the deep learning, okay, because they have to take care of something that was first taken care by the human, by the expert. So they are usually bigger, but not just a bit bigger, they are much bigger. And in general, if we just look at the neural network, what makes the difference between a neural network and a deep neural network is the number of what is called the set of hidden layers. Okay, you can imagine a neural network like, as I said before, a connection between different nodes, but those nodes are usually organized in layers. Okay, so this is the input layers where the input comes in. You have an hidden layer where the reasoning, so all the combination of stuff is happening, okay, and then the output layer that is giving you the output of the reasoning, okay, under quotation mark, of the machine. Okay, in the neural network, not a deep neural network, the hidden layer is 1. Okay, if the hidden layers are more than 1, then by definition is a deep neural network. Okay, it can be 2, 3, or 1,000 is deep neural network. Okay, of course, as you can see from this picture, just passing from one hidden layer to multiple hidden layers multiply a lot the number of the connection. So remember, the connection are actually the parameters of the network. So are the weights that we have seen before in the sum that is doing the system. Well, the more is becoming deep this network, the more these parameters are booming out. And in fact, when we have sites that is around thousands of parameters in a non-deep neural network, in a deep neural network, we are talking about millions, billions. Okay, LLMs are in the billion, okay, or trillion of parameters. So we are really talking about monster models, okay, that will take a lot of hardware to run. Let's understand a bit about, because as you have seen before, we have this layered structure, okay? And I also told you that this layered structure can help in doing what the human are doing with the machine learning, so understanding the features. So this layered architecture is really you can imagine it like a progressive abstraction of the problem and a progressive extraction of patterns, okay? So imagine that you have to do a model that is taking pictures and the model has to decide if it is a cat or not, okay? So in the very input layer, you have the raw pixels, okay? So you can imagine like a matrix. Every point of the matrix is a value, okay? So the system see a matrix, okay, a table filled with values. Then the first layers of the systems, of the deep neural networks, are really the ones that are understanding, thanks to their mathematical properties and their values, the very first kind of elements in the very primitive elements of the picture. So they will recognize, okay, the presence of an edge, maybe they will see an arc, maybe they will see a little circle, maybe a point, maybe an angle, all these basic elements. Then layer by layer, this basic brick of graphic, because here we are intending an example in the computer vision, are combined to extract higher level features, like, I don't know, okay, if I put an arc with a round, it seems like an eye. If I have an arc, maybe near the eye, it's an eyebrow, and so on. And you start to combine more and more of these elements until you see you have recognized the face of a cat. So at the end, you have mapped, you have extracted this information, okay, of the presence of a cat. And you can say, okay, it's a cat. So the system can say it's a cat. Of course, this is an oversimplification, okay? So what you see here that is depicted with something that we can understand. So lines, angles, eyes, the face of the cat. Since it's not controlled by a human, since from a certain point of view, these models are black boxes, what the meaning of these intermediate features sometimes is not understandable by you. Okay, so you will see something that doesn't make any sense for you, but for the network instead, it makes sense because it helps to solve the issue. Okay. Finally, okay, we are almost arrived to the end of this set of nomenclature. In the deep learning domain, because it's only possible with deep learning techniques, we have what is the generative AI, okay? What's the difference among the two? Of course, deep learning is a family of methods, okay, that can do many things. Can do classification, dogs and cats I was saying before, prediction, maybe you put as an input the picture of an house, or you put as an input, I don't know, market trends, okay, and it will predict the next value. Or can do regression, maybe you put the video of I don't know, a ski performance, and will regress what is going to be the final mark, or etc. For example, you can classify a protein as an effective. In the generative AI instead, that is still deep learning, is the task that made the difference. Okay, so among the different tasks that the deep learning is able to perform, there is one that is particular, that is the generative task. That is a bit a change of point of view, okay? Because in the non-generative AI, you provide data and the system is taking you out the performance of a task, okay? So as I was saying before, the class is going to tell you the next value in the stock market, and etc. In the generative AI instead, the system is not as an output giving you this stuff, but is giving you something that is new data, okay? If you write to ChatGPT, ChatGPT is writing you back, okay? So it's creating data that is similar to the data that you give to it, okay? In a way that it seems like it's original data, okay? So apart from some case, okay, apart from the niche, okay, in general, if you read something from ChatGPT or Claude or like, I mean, all these applications is hard if you don't know the context, okay? It's not so simple to understand that it's from a machine, okay? Because it's really similar to the data that you put in, okay? So that's the difference between the other algorithm, okay? And this is really where it changed the paradigm. Here there is the example of protein. While in the classical deep learning, you have a protein like this 3D structure or its expression, and you ask the system, okay, tell me what is the probability that this protein is effective for this task. For a generative application, maybe you will ask, okay, I need a protein that is effective for this disease, and then the system will create you the protein, okay, that is the exact flip of what I was saying before. Now, the LLMs, okay, so because in this presentation, I'm going to focus a bit more on this because it's a lot talked, okay. In the LLMs, that are generative applications that generate text, okay, because you can have generative AI that do many things. You can generate proteins, you can generate videos, you can generate images, you can generate other data, okay, tabular data, you can generate many things. But LLMs are one that are actually large language models, so they're really about the language. They generate text, okay? And they are in the big field of tasks that is the natural language processing. You see here, okay, that the natural language processing is not a subset of some of these, but it's really crossing all the subsets, okay? LLMs, of course, are in the intersection between the natural language processing and the generative AI. But really, with natural language processing, so this is the difference between NLP, that is natural language processing, and the LLMs. The difference is that LLMs are generative application for natural language processing. NLP is the broader task and can be done in many things. Can be done with generative AI, okay, but can be done with machine learning, or can be done with artificial intelligence, okay? Can be done in many ways. Because if I have the task to recognize if in a text there is any reference to, I don't know, for example, dangerous stuff, I can just I can also do an artificial intelligence system that is not using any fancy algorithm, but is just checking the presence of a catalog of words, okay? And maybe it's enough for my application. And it's not, of course, machine learning is more a symbolic application, okay? So you can solve the natural language processing tasks with basically the whole artificial intelligence set of tools. But if you're talking about LLMs, you are exactly talking about the generative AI tools in the natural language processing. Okay, now I talked a lot already, but there is still a bit to talk. So we said that those systems, okay, requires data. So for now we are focalizing on the machine learning set of algorithms, so the one that really learn from the data. To make the action of making this model understanding from data is referred as training, okay? So the training of a model in general. Model on a broader scope, can be a mathematical model or an algorithm. In the recipe for doing this task, you have some super basic elements that you need to have, okay? And then you can combine in different way to do your task, okay, to do the goal that you want. The very first, of course, we are talking about data-driven approach in the machine learning, so is the data. And the data is composed usually from examples, okay, where the system can learn from. And for having this in an efficient way, it's very important that they are enough in terms of volume, that they span around the whole variety of case that you can encounter. They are of good quality, okay, because of course, garbage in, garbage out, so they must be curated. They must be meaningful for the task that you are that you want to achieve, and they must have some balance. If you have different classes inside, different groups inside your data, it's important that you try to find a balance okay, among the different categories, okay, to do not make the model learning some bias that comes from the unbalance of the data and not from the real problem. Then, of course, apart from the data, you need to have a goal, okay? So you need to have a task. So you want the model to do something after training, and there is a complete set. So here I put some examples. For example, we talk about classification task when the model is asked to classify an input between different categories, or we can have a regression that is instead an estimation, a numerical estimation based on the inputs, or you can have planning if you have to, okay, I give you a situation and you have to give me the steps that I have to follow to reach a goal, or you can have the generation that is the generative AI that we were talking about before. Then, of course, you have the model that is the subject of this training, that is really the structure that we learn from this data that are usually composed by mathematical models. We have seen before neural networks are weighted sums, okay? You have the iterative algorithms that allows you to have this model working and learning. And you have also a lot of statistical models and methods to make this stuff working, okay? Finally, this is really important. So this is really the glue that makes everything working, that can influence everything, is what is called the loss function. Okay, the loss function is a measure of the performance that your algorithm, that your model is having on a set of data for a specific task. Okay, you can intend it as a KPI. Okay, it can be, for example, I don't know, the accuracy. Accuracy, you will find. I'm not saying it, but in these slides, but accuracy is not going to be is not a loss that is usually used, but some mathematical definition that are a bit more complex, okay? But the loss is really the one that is governing, that is driving your training, okay? The only goal of the model during the training is to minimize the loss, because loss is usually the higher, the worse, the lower, the better. So the entire thing the model is doing during the training is given a data, calculating the loss, and changing its own parameters to minimize the loss. That's all, okay? So that's the model what it's doing. It's only focusing on the loss, nothing else. And this is an iterative approach, okay? So you have a model, you perform the task with the data, with the training data you have with the model. You measure the performance thanks to the loss, using the performance that you have had. Then you tune the model to lower the loss, to improve it. Now you have another model that is the new model with the new parameters, and you do again. So you have cycle by cycle. The idea is that you will make the loss lower and lower. That means that the model is better and better in doing the task. A couple of things, okay, because this seems everything is nice, but of course maybe you already know, maybe you have understood from what I was saying, but I will tell anyone anyway. There are some strange things that can happen that are because the way that is built, okay. The model, of course, has no clue about the world, okay? It's just a mathematical machinery, okay? Sums or whatever, okay? And doesn't know what is correct and what is not, okay? So the model can only learn what you show them, okay? If they learn, they only learn, of course, what you show them. So this means that the variety of your data of training is really important. If you sorry, if you, for example, build a model that is able to estimate the cost of an house and is only trained on houses that are, I don't know, Italian houses, okay, maybe in the southern Italy, okay. If you take that model and you will ask the model to make the same estimation of an assassin house that is completely different, that is in German, between the Germany and France, it will fail, because I've never seen that kind of house with these big roofs, you know, it's with these wooden details that are completely different from the houses that are in southern Italy. It will completely fail. It will invent, okay? It doesn't know, because the model is completely blind to what is happening outside what they've seen. So you see here the meme that is basically say, okay, I prepared a very good model in understanding dog and cats, but I forgot to put this Sphinx cat that is a bit different from the other cats, and so the model is not able to answer because the cat is completely different from the one that I've seen. So it's really important that the amount of data, but also its variety, is good enough to have a good training. Second, that is connected with the first, the model is completely dumb. Okay, so it's, as I said, I repeat, it's just a set of mathematical combinations. Okay, so you throw the data, will trust the data blind, it doesn't know what. Sorry, the model doesn't know. Okay, what is correct or what is not. It's taking, okay, what you give me is correct by default. Okay, so it's really important that the quality of the data is good. Okay, because if you put garbage in, you will get garbage out. And also is important that the loss function that you choose to close the loop is representative of the problem that you want to solve. Okay, should be the right one. Finally, the model is only caring about the loss. That makes it extremely greedy. So has no clue and is really just interested in the loss. Doesn't care anything else. So it will find the best way to minimize the loss. This means that sometimes the model can take decision, okay, that can shape itself in a way that seems like is good because the loss is minimizing, but in reality is not really capturing the essence of the task that we want to solve. I will explain you with this example that is a famous example in the literature. So imagine that this model has been trained to recognize husky dogs from wolf. Okay, so has been trained with a considerable amount of pictures of huskies and wolves. Okay, then they did the training. The results were really good. Okay, it was really good in the data that they have in recognizing the huskies and the wolves. But sometimes it fails. Okay, you see here the failure. Okay, this one in the last row on the left. So the researcher here asked themselves, okay, why it failed in this situation? Okay, because this is an husky. Okay, it's quite clear. So to do that, they use some techniques that can look into the model to see which part of the picture were the really important one used by the system to understand, to discern between the dog, the husky, and the wolf. Okay, so they were really curious to see, okay, but how the system is able to understand the dog from the husky. And they actually find out that the model to detect the wolf is not looking at all at the enemy, is looking at the snow. Okay, so this means that the system, because it's only caring about the loss, it found out that was much simpler to look at the snow to recognize wolf, because in the data that was provided to the model during the training, all the picture of wolves were taken with the snow. Okay, so the model understood that if there is snow, then it's a wolf. So what happened if you put an husky with snow? Is saying it's a wolf, but it's an husky. Okay, while for the husky, you see that instead he's looking at some particular part, okay, of the body. Okay, you see the eyes, you see the ears, you see some part of the fur. Well, instead for the wolf is always about the snow. Okay, so you must be very careful in designing your training because you have to avoid this bias. I made you the example now of the wolf and husky because it's quite famous. But if you look at the other example, there are many, there are plenty. For example, in medical imaging in human, there was plenty during the COVID. The system is if you provide, if you, for example, collect all the healthy people with one machine and all the sick people from another machine, a radiological machine, even if maybe you look at the picture and you cannot see what is from which machine, the model is able to understand the machine and just doing the same that has been done with the snow. If the machine is the second, then it's sick, with not looking at all at the picture, okay? What I just explained, so the greedy and I mean the fact that the system is really overlooking what you have throwing out is also called overfit. Okay, so the model has learned too much from the training data, has not been able to separate the noise from the real information. Okay, the snow in the wolf husky problem is noise. Okay, it's not really the task that you want to solve. It's noise. But the system learns from the noise. That is really what we don't want to do. If you have overfit, you will have excellent training data performance, but in the real life is unuseful. Okay, the model is unuseful. On the other side, you have the underfit. Okay, if the model is too small, is not capable enough. If the data are too small or the loss is completely irrelevant, then the system will also be bad in the training and will be bad everywhere. So it's bad performance over. Okay. The entire recipe of the training is to find the right balance between the underfit and the overfit. That is the sweet spot in the middle, where you learn the core function that you want to learn. Okay. You see here in this example, this is of course underfit because you have the points are the training data, okay, so the data that you want to model, and the line is the learned function. In the first is underfit because you see it's an approximation that is very bad. On the right you have an overfit because the system is really tracking every of these points, but is really following everything. Okay, so if you put something here, it's telling something very wrong. Well, instead, the optimal is this one, in which you kept the core pattern in the data and you model it. Okay, so the sweet spot between the underfit and the overfit is really the goal of designing a training procedure. Now, if you take all the stuff that I said, all the ingredients that I was telling you before, you can have different recipes of training that you can apply to the different problem that you want to solve, depending on what you have as a data. So imagine that you have very classical data. So you have a table with a lot of samples, or you have a lot of big pictures, and you have what should be the expected output. Okay, so you have samples and expected output. What you can do is to have a model, as I said to you before, that perform the task. Then you have to predict the output. You have the loss function, you have the training algorithm, and the model improves based on the difference basically between the expected output and the predicted one. So you want the loss to be smaller and smaller. And this is the well-known, I mean, it's well-known, who knows it, okay, but if you don't know, this is very diffused, is the supervised learning, because you're really supervising with providing any expected output. And this is the classical one. So you have dogs and cats, you throw a lot of pictures of dogs and cats with labeling, with saying to the model which one is cat and which one is dog, and the model will find a way to figure out, of course, with all the stuff that I said before about the greediness, overfit, and outfits. But what happens if you don't have any label? Well, it happens a lot of time, okay, because especially in the veterinary field and the human medical field, it happens a lot of time because maybe you have a lot of data, but labeling it, so providing an expected output, it's something that requires a lot of involvement of specialists that are not that available, okay? And will take a lot of time. So usually you have a lot of data that are not labeled. Well, the very first thing that you can do is the so-called unsupervised training, okay? In the unsupervised training or learning, okay, you can usually use. You just use the samples. You perform some tasks that is usually classification, clustering. You will see an example in the next slide. And from that task, you will extract some statistical properties, okay, of the output of the task. And what is usually called the loss here is called the fitness. You try to optimize the model to improve this fitness, okay, of statistical properties, okay. Maybe with an example is easier. So imagine that you start from the one on the left. Now there are just points, okay, in the two-dimensional space. You don't have any label, okay? What is what, you don't know. But you want to, maybe, I don't know, this is, those are customers, okay? This is the time spent on your platform and the money spent, I don't know, just two-dimensional. And you want to say, okay, but can I identify categories, groups of users? Well, with the clustering algorithms, that is one of the unsupervised methods, you can classify the users, in this case, these dots, based on their proximity. So you say, okay, these blue are one each near each other, so they are one class, these other one are other class, and these other are other class, okay? You're not saying exactly what class is this, what class is this, and what class is this, but you basically clustered, you divided into classes based on their pure statistical properties, okay? Then you can go afterward and see what is into these sets, and you can define a label for it. But if you don't have the expected output, you can also do something else that is a bit more complicated. You can create a pretext task that is not really a task that you have in mind, okay? It can be a task that you are inventing, okay? But it's a task that you can determine from just the samples and expected output. With this, okay, you can do the same loop that we have seen before for the supervised learning, okay? But in this case, your algorithm, your training is creating the expected output by its own, because in the data there are just the samples. This is particularly relevant because we will see it is a lot used in the LLMs. And here you can see an example. So imagine that you have a lot of pictures of landscapes, okay? You don't have a clear task, but you just want to have a model that understands the landscape. Or imagine that you have 1,000 pictures of landscapes that are labeled by the place on the earth, or maybe the hour of the day, okay? And you have 1 million pictures of landscape that are not labeled, okay? If you just do supervised learning, the 1 million pictures that are not labeled cannot be used, okay? Because you don't have the label. And so you have just to train with those 1,000 labeled pictures. With self-supervised training, you can do a sort of pre-training of your model. So usually self-supervised training is used a lot in combination with the supervised one. So usually you do very big self-supervised training with a lot of pictures that are not labeled, and then you just do a small training supervised that is called fine-tuning on a little set of labeled ones. But during the very first part, your goal is just having a model capable of understanding the data. Okay, so in this case, for example, you can take all the picture of your landscape, you can crop one part, and you can ask the system to fill it. Okay, by doing this task, the model is forced to understand the landscape. Okay, it's not really capable of doing something. It's not yet capable of understanding which hour. Okay, but you remember the layers, no? In its layers, is starting to extract meaningful features that can be useful also for the task that has to do. And like this, there can be, okay, cropping of part, asking in painting, you remove the color and you ask to put the colors, or you take the picture, you rotate it, and you ask the model to predict how much has been rotated. For example, here is very simple. Now you rotate and you ask to the model, okay, tell me what is the rotation. But to do this, the model has to understand that an airplane has a tail that usually, and on the other side there's an head, that are the wings. That usually in the tail there is a little wing here that is on the top, that if it is under means that is being rotated, and so on. Okay, so to do this has to understand many things. That can be helpful anyway. Finally, we have a bit different from the others, setting in which we have no data at all, okay? We only have an environment to interact with. That is the reinforcement learning. In the reinforcement learning, the model is performing some task, okay? This task have an effect on an environment. The effect is observed and is elaborated, analyzed to understand how good it is respect to a goal. Okay, you only have a goal and an environment. Okay. With this loop, the model improve its policy of understanding which action to perform, to the point that is going to be better and better. For example, here you see a research that has been made some years ago, where a model was provided a body, a virtual body, okay, and was asked to the system, okay, learn to run and to avoid obstacle and to jump and do many things. In the very beginning, in the very first iteration, of course, the model is barely able to stand up, okay, then it's falling down. After a few iterations of the loop that I was showing you before, the system is able to run on the stairs, avoiding the obstacle, you see, is able to jump over holes. Of course, it's a bit goofy because it's learned to move like this. No, it's quite funny, funny or terrific in the way that you want to see it. But it learned by its own. So it's working this way because it's learned completely by its own. No one said, okay, this is the way that you have to learn to work. So it tried multiple times until the reward that we have seen before has become so high that is pointing to the right direction. Okay, and this is the reinforcement learning, because through different reinforcement you learn to basically react with the environment. That is something similar to what happened to the humans. Okay, because you do stuff in the world, then maybe you feel pain or you feel happiness, and you try to your reward is about pain and happiness and other things that we feel. Okay, and so we learn. So imagine that you have to learn to walk. Okay, you fall many times until you find a way to walk. Okay, and then you start walking better and better. Okay, you start to run, you start to jump, and etc. Okay, now I put a lot of ground. I know I said many things, but now we can go back to the LLMs. Because really here, the point is that LLMs are generative AI application for natural language processing. They feel like they are intelligence, okay? They are intelligent. They feel sometimes like they are thinking. We have said before, I said that is just mathematical stuff, okay? So it's not really thinking. So when we say that the LLM is thinking, okay, so when LLM is replying us, what exactly is doing? We will see in a while. Just few points about the LLMs. Remember, they are trained on enormous amount of data. Okay, you can see many different data. This toilet paper is also not by chance, but also because sometimes there is something bad. They just rely on exploiting the statistical patterns in the language. We will see in a while they build their answer piece by piece, and they use a specific architecture of neural networks that is called transformers. Okay, now there are also other architectures that use, but basically the most of them are transformers. I'm not going to the details of transformers, but just think that they are architecture made in a way that they can focus between relationship between parts of the input that are called tokens. So the input is split into tokens. They are heavily relying on large scale self-supervised learning, pre-training, as I was saying you before. They can capture, because of this relationship between the input, large input efficiently. They are very good in doing sequences because they are doing piece by piece, and they work in an auto-regressive way that we will see in a while. What does it mean? This is a bit of okay. This is there are some details that maybe is not going to be very easy to understand, but there are some steps that we will see with an example. Okay, so imagine that what is happening when you ask to an LLM, is the apple a fruit? Okay, the very first thing that the model is doing is splitting the input into tokens. Okay, as I said before, tokens are not really words, can be part of that. So for example, here you see some separation with these colors. And to each of these tokens is assigned a number, okay, a value. That depends from the kind of word, but also from the position in the word. Then the system is doing what I said you before, so finding relationship, okay? So it's trying to understand, okay, in the word, what is important? What is important in the input? Is the and are the articles important or the space important? Not that much. But what is really important in this phrase is apple and fruit. Of course, I'm imagine this is just for presentation. Okay, it's a bit more complex than this, but it's really saying, okay, is apple fruit is really the core of the question that is being asked to the model. Then the system is using this fundamental piece of the input to say, okay, now I need to predict my answer. Okay, and I will predict it piece by piece again, so token by token. So if the question is the apple a fruit, considering that is apple fruit is the core part, what is going to be the next word, the next token? The next token, you have a model that is being trained to predict that the next token is yes. Okay, if you write is the dog a fruit, is going to be no. Okay, because with this input, usually this is the output. Then the model, what does it do? It takes this yes, that was the output. It put also this in the input. You see that the yes is going back to the input, and is doing again the same trick. So it's saying, okay, what's the core part? The core part is to understand what is coming after yes is just yes. Okay, because after yes, you know that there is a space, and so is calculating the space is the next one. And iterates one over the other up to the moment that it composes the answer that we have seen for a while. Unfortunately, this tool is not allowing me to going back, but is building block by block. Okay, as I said you before. So sorry, I would like to keep the slides a bit more, but I will try to do by words. You have seen very fast that this mechanism is just step by step. So LLM is not really thinking. Okay, it's just predicting what is next based on what I've seen in the gigantic amount of data that you throw out, that has been thrown in during the training. Okay, so the model have seen that somewhere in the system there is written that apple fruit yes, oppure or sorry for Italian, apple fruit, if there is and a question mark, the answer is yes. The answer will start with yes. It learned that after yes there is a space or a comma. It learned that after the comma and the yes, if there is in the question, then there should be an is also in the answer, and so on. Okay, so it's just connecting the dots in the gigantic amount of stuff that has been trained with. Okay, in fact, the training of LLMs, and here I'm oversimplifying because of course the biggest players they are not really sharing their secret recipes. Okay, so I'm just telling you what is known. Okay, LLMs are usually trained in 3 steps that are using different amounts of data. There is a pre-training that is using the self-supervised learning, where really the system is just trained to predict the next token. So very simple. You are giving it Shakespeare, and is just able to predict what is going to be the next word in a Shakespeare stuff. You are providing it science articles, and is learning this stuff. By doing this task, this action, the system is really doing the learning that we were saying before. But it's not really learning to think. Okay, the thinking is because somewhere is written a thinking. Okay, so is not a direct. It's not something that is happening into the system natively. Okay, so in the pre-training, the model is just the so-called language model. So it's a model that is just modeling the language. Okay, nothing more than this. It's not aligned. It's not optimized to produce a dialogue. It's just very able to. It's memorizing stuff. And when you do that, you need to throw out an enormous amount of data. We are talking about thousands of trillions of data, okay, of samples, gigantic. In fact, you know, enormous energy problems because of these data centers, billions of dollars spent by OpenAI, by Anthropics, by everyone to train these models, because they are really resource expensive, okay, to do this stuff because of the volume, okay. But those models are not ready, okay, to be provided to the public. They must go under the fine-tuning part. In the fine-tuning part, you have, instead of having just text with no labels, nothing, so text taken from the internet, from Reddit, from Wikipedia, from whenever, okay, wherever. In the fine-tuning stuff, the companies have some instruction-based data. So you can imagine that you have questions and answers, okay? And so you are training your system that is starting not from scratch, but is starting from the language model of the step before, to say, okay, if you have this question, then you have to answer this way. And the system is capable of learning this, so it's refining itself to be a question and answer model, not just a phrase completion, okay? And this is the supervised training, okay? The supervised fine-tuning LLM. This is capable of answering questions, okay? Is no more a language model, is capable to answer your questions, but is not really, is not yet human ready, okay? During this phase, you use diverse order of magnitude less than the previous step, so but you still use lot of data. In the final step, there is what is called the alignment. Okay, so you're no more interested in just complete the text. You're no more interested in having a specific output. You want that the output is human, is aligned with the human preferences. Okay, so that the words are composed in the right way, that is not rough, that is not suggesting you strange things. That means that is human, aligned. One of the techniques that is used for this is the reinforcement learning we have seen before, but this time the environment is represented by a human that will give you feedback. They will give feedback to the model. Okay, I like it, I don't like it, I prefer this, I prefer these others. And if you have used ChatGPT or Claude, you know that you have the thumbs up and thumbs down. You are exactly doing that stuff for them. Okay, so you're aligning the model to your preference. And this requires much less data, also because you have humans in the middle, so you cannot have millions of humans doing this work for you, even if ChatGPT is doing it. Okay, we are almost at the end, okay, I promise. AI is fantastic, okay, it's a fantastic tool, it seems like magic, okay, a lot of time. LLMs are really having an impact, okay, they are really useful. Okay, I said you that I'm not really reasoning, but the way that they can tackle some work you have seen is very, very good. Their impact is extremely strong, but we have to be careful. We have to know them, okay? Because we have to know what we are using, because we have to understand that they do not understand the meaning of what they are saying, because they are not really reasoning about that. That they can be very convincing in giving you fake news, because they can hallucinate facts, because you remember there was the language model section of the training that makes them extremely strong in writing good, okay? So you can be really convinced of what they are writing, so you have always to oversight what they are saying. And also you have to really ground it to the literature, especially if you're working in a niche. For example, the veterinary niche is really something in which the generalistic LLMs are not capable, because they have not had access to so many veterinarian literatures, okay? So this is really where they start to fail, okay? Because they can also reflect some bias in the training. So if in the training data you have racial bias or other bias or gender bias, in the output they will reflect that bias. For this reason, in the veterinary field, we define in AITEM, we designed Leica. Okay, that is the tool that we do, that Sarah was so kind to say some words before. Leica is an AI assistant for vets. Okay, so it's specifically designed for dogs and cats. We took care of each of the stuff that you have seen on the left to make it forcing to use clinical reasoning. Okay, so we force Leica, we engineerize it to be really following clinical reasoning. So to always ask itself if it's doing the right thing, to always ground to scientific stuff. Okay, so we are Leica is trained and is prepared with much of updated veterinary literature, and not also, but this is not enough. Okay, Leica is designed to do support, not for replacement, because it doesn't make any sense for all the reasons that I said you before. This is a really important message. So Leica is capable to provide value only if it's used with the vet. Okay, this is really the vet in the middle should be always true, because it's really something that should make the life of the vet easier, but not replacing them. So let me say, to remove all that stuff that is not really important, okay, that is maybe just taking you a lot of time, okay, that can be done more efficiently, or also to provide you some support. Maybe you don't have the latest updated guideline, and Leica has it and can give you, okay, and you can, okay, I read the output of Leica. I am always critic about what Leica is saying. I'm a vet, I can understand it, and I can get value from it. Okay, so this is always something to keep in mind. This was something really that we made when we designed Leica. Leica is doing many things, okay? And you can also imagine that in the veterinary fields, you can have an enormous amount of application, okay, that are trying to cover in different aspects. Okay, yeah, I listed some of them, because you can, you have application, sorry, you have application in the AI, maybe some of you already seen it, that supporting the onboarding of the clients or the triage. Okay, so that you have some AI that is keeping care of the communication with the clients, for example, or is helping in the schedule of visits, or is doing some administrative task. Okay, or is also listening to the visits. Okay, and is, for example, giving you some summary of it, or like is giving you clinical suggestions, or is reading your laboratory results, or is providing you analysis of the imaging, or is writing you the discharge. So you can have many things in the generative AI. This is, everything can be variable. With Leica, we concentrate on the central part for now. So Leica is able to have the clinics, of course, that is really in the center, so it can provide you any suggestion, diagnostic, follow-up, next step, whatever. It can interpret laboratory results. It can listen you can record your visits, and Leica can give you a report in the end, and you can discuss with Leica about the case. can support some kind of discharge note, not completely, we're working on it, but we have the plan to cover the full spectrum. So in the next months, Leica is going to cover everywhere is needed by the vets. So to make the vets really concentrating on what care the most, that is the relation with the owner and the pet. Okay. So let me. I don't know if I have the time to show you a demo, but I try to be very fast. Okay, so let me just doing this while doing this to be very fast. Okay, oops. Okay, so this is how Leica looks like. So you have the patient that you have created. We can create a new one. We can call it people. Owner is Mario Rossi, and the patient can be people. Sorry for the Italian, but I'm using it. Let's say that is not sterilized, so I can create a patient. I can say that is a dog, and I can say that, for example, as almost 2 years old. Okay, so it's 2023. So now I created a patient, and I can start chatting about it. Okay, about this patient. So, for example, I prepared some. Sorry, I prepared some questions. I'm not much good in inventing, but imagine that you want this dog arrives to your clinic and you suspect leishmaniasis, okay, and you want to know what to do next, okay. Now, maybe this is simple for you, but you can imagine something more difficult. I'm not a vet, so for me it's already difficult. Now, Leica is elaborating the information about that, is grounding to the literature, and is telling you what to do next. So it's telling you that you have to do a clinical assessment, that you have to do some laboratory check, that you have to what to do next, what to check exactly, and is proposing you a long list, okay, of actions, okay. So you can follow it, or you can, more important, read it and be critical about that and analyze it. You can exchange many messages with Leica. You can really argue with that. You can exchange. You can try to put your point of view and etc. Imagine that we had this stuff, and then we said, okay, sorry, another one, that is this one. Okay. Oh, I put this one. Okay. So something that also is really appreciated by our user is asking about the dosage of pharma. So imagine that you have the doubt. Leica is taking information from really the ground truth of the you know, the compendium or stuff like this. Okay, so the real approval documents, and is taking out the information about the dosage for that specific disease. Okay. Now imagine that I can also do other things, like I can upload a document. For example, I can upload a blood exam. Now Leica is elaborating the PDF and is extracting the values. It takes some seconds to make it, but it works. If it's not, I'm going back to my team and say, okay, it's not working. 99% of the time it's working, it's just taking some time. You will see in a while that you see it. This is the document that I uploaded. Those are all the values that has been extracted by the system. And when I confirm that I checked that everything has been taken correctly, Leica is connecting these values with the case that I presented before. Now, since I'm mixing up a document from a patient that was not the one with the leishmaniasis, is making some, is finding some not connected items, so is giving you. But you see, the idea is that is giving you its interpretation. Let me go back to the slide. So let me close. Okay, this is the last slide. So the idea is the following. Leica is one tool. It works only if you are with Leica. This is a general stuff. It is also only working, is also only working if it is integrated with the whole IT ecosystem that you already have in your clinics. And you see here some example. Leica is already working integrated with some PIMS, okay, PMS, is already working integrated with some laboratory systems, and we're working to include more, so that really the vet is just talking with Leica, and Leica already knows, because it's already connected with all the source of information that can provide everything. Last slide, as I promised, just thank you, okay, for being here. I talked a lot, I know, and I feel actually, but now if we still have time, I will be very happy to answer all the questions we can. If we don't have the time, write me for any question. You will have the presentation, so you have my email, or otherwise you can find me on LinkedIn and you can write me. To excuse you for having talking so much, if you want to try Leica, you can use this discount code. You can register, okay? This registration is free. You will have 7 days free trial. If you like it and you want to try it more, you can use this discount code that you see here, and you will get 1 month with 75% discount, so that you can test it more and more, okay? And will be very good for us, because we want to know your feedback. We already have good feedback from the field, but it would be great to have more people in our user community, okay? And that's more than all, I think.
Amazing. Thank you so much, Davide, for that really comprehensive overview around AI in veterinary. And hopefully a lot of you took a lot away from that. We are a bit tight on time, so I don't know if there's any urgent questions in the Q&A that everyone has. I'll have a look. Can't see any urgent questions. You probably covered absolutely everything in that session, but I know, as Davide said, if you've got any other questions, feel free to email us and we can send around the information that we went through during the deck. Just a quick plug before we break to say shares from.
By the way, in the meanwhile, I'm going to write my email in the meeting chat, so that if someone wants to write me directly, they can write me.
Yes, that'd be perfect. Thank you, Davide. And it was just to let you know that we have our Incubator Showcase event happening on the 27th of April this year in London, Canary Wharf. So if you're interested to find out more about the other innovative technology like Leica and AITEM that are happening in animal health, we'll be having this event in the evening in level 39 Canada Square. So what you'll get there is to get to see some pictures from our newest cohort who are joining next week, as well as a senior representative keynote speaker from Zoetis, which is very exciting, as well as just general networking for people in the animal health ecosystem. So if you're keen to join, there's a QR code on the screen there, and we'll be able to send more information about that as well. But that brings us perfectly with a minute spare to time. But if you've got any other questions that you'd like to ask about the programme, or to Davide about Leica or AI more generally, we'd love to hear from you. But otherwise, thank you so much for joining this session this afternoon. Hopefully we'll be in touch with further webinars like this throughout the year. And with that, have a lovely afternoon. Thanks so much, everyone.
Oh, goodbye.